All right, in the previous video, we looked at this method for finding a basis for u plus v and u intersection v. Now, in this video, we'll be proving the following proposition, proposition 1.5.4. Let u and v be both finite dimensional subspaces of the same vector space. Then the dimension of their sum is the dimension of u plus the dimension of v minus the dimension of the intersection. All right, so I want to prove this. We're going to use the method that we just learned to prove it. So to simplify the argument, let us prove this result for a subspaces of En and assume that we have these bases. All right, so notice that that tells us what the dimension of two of them are. So dimension of U is K and dimension of V is L. All right, so let's assume that we put all of these vectors in a basis and reduce, and let's say that we get R1 for the U's and we get R2's for the V part. All right, so let's take R to be the rank of the reduction. So if we the dimension of the sum, then what we'll be using is that U plus V is the span of U1, U2, V1, V2, and so on. And so when we reduce the matrix A, what we end up doing is taking the vector that correspond to each leading one of the reduction. And so we keep one vector for each leading one in R1, R2. And so the dimension, the number of vectors that we'll keep, that's going to be the dimension that depends on the number of leading one, and we call that R because that's the rank. All right, now let's look at the intersection. Right, so to get a basis here, we start with, it's not quite A. We're going to start with U1. That one was fine. U2, that's fine. Up to UK. I don't change anything here. But then when I bring the V's to the other side, I end up with a minus. All right, and when I reduce this, if I do exactly the same row operation that I have here, well, I'll end up with R1 and then minus R2 as the right part. But that minus doesn't change much, right? It doesn't change which entries are zero. It doesn't change which entries are not zero. So this is in REF. It's no longer in RREF because by multiplying by -1, you end up with minuses. And let me show you when we see it in this example, right? If you take exactly the same reduction, you end up with this. So these are flipped. In fact, all of these are flipped, but it's not in RREF because that's a minus instead of a plus, but that's fine. You could flip it. But even here, you can already know that I'm going to keep three vectors because that I have rank 3 because I have these three leading entries. All right, so here this is in REF and it has the same number of leading ones, a leading coefficient of R1 minus R2 is the same as the number of leading coefficient in R1, R2, and so it's the same as R. All right, so the rank of this matrix is still R, but that's not the number of elements we'll take. We'll take a generator for each free variable. And so the dimension of the intersection will be the number of variables minus the number of leading entries. And so here that's going to be, well, number of variables, let's see. We have K plus L. So K plus L variables. So that's going to be k plus L minus R, right? But k was the dimension of U, L was the dimension of V, and in part one we proved that R was the dimension of U plus V. And so if we rearrange this, I mean, this would be a fine equation, but I tend to think of it as U plus V equals something. So dimension of U plus dimension of V, and then I'm going to have to switch and get the. All right, that's it for this proof.